A telescope 1 million miles from Earth just found a comet older than our entire solar system. Not older by a little, older by 3 billion years. That is not even the strangest thing it has found since it opened its eye on the universe. This is everything the James Webb Space Telescope has actually discovered so far. No exaggeration, no filler, just what the data really shows. Webb launched on Christmas Day in 2021 and began real science operations in the middle of 2022. And in the years since, it has quietly rewritten entire chapters of astronomy that scientists thought were mostly settled. It was built to do one thing better than any telescope before it: see an infrared light, which lets it peer through cosmic dust and stretch its vision back toward the very beginning of time itself. That single capability is the reason almost everything on this list exists at all. And let's start at the edge of time, because that's where Webb has caused the most trouble for physicists. Within its first year of operations, Webb spotted galaxies that had formed roughly 300 million years after the Big Bang. Capturing light that had been traveling toward us for over 13 billion years, the oldest light ever directly observed by any instrument humans have built. That alone would be a headline on its own. But then came the part nobody expected. These early galaxies weren't small, faint, barely formed smudges, the way the leading cosmological model predicted they should be. They were big, structured, mature-looking, in a universe that was supposedly far too young to have built anything that developed yet. Astronomers started calling it the impossible galaxies problem, and it's not an exaggeration for once. The standard model of cosmology, the one built on decades of observations and called lambda CDM, simply did not predict galaxies this large and this organized existing this early. Nobody has fully solved this yet. Some researchers think galaxies formed stars faster in the early universe than current models account for. Others think there's something more fundamental missing from the model of how matter clumped together after the Big Bang. Either way, this is one of the biggest open questions in cosmology right now, and Webb is the telescope that created it, simply by looking further back than anyone had looked before with this level of clarity. Connected to that same mystery is something Webb discovered almost by accident: a strange population of compact, reddish objects scattered through the early universe that astronomers nicknamed little red dots. First spotted in 2022, these objects didn't fit cleanly into any existing category. They were too small and dense to be normal galaxies, but too bright and structured to easily dismiss. Years of follow-up spectroscopy have gradually connected pieces of this puzzle together, and current research suggests at least some of them may be a previously unknown phase of galaxy and black hole growth happening in the extremely early universe, a kind of missing link scientists didn't know they were looking for until Webb accidentally handed it to them. While cosmologists were busy arguing about the early universe, a completely different team was using Webb for something much closer to home in the grand scheme of things, figuring out what distant planets are actually made of. This is where Webb has arguably done its most consistent, most prolific work, because unlike galaxies from the dawn of time, exoplanet atmospheres are something Webb can study over and over, planet after planet, building an actual catalog instead of chasing isolated headlines. The very first proof of concept came in 2022, when Webb captured the first clear evidence of carbon dioxide in the atmosphere of a planet outside our solar system, a gas giant with no rocky surface, orbiting a star hundreds of light years away. It sounds almost simple compared to what came after, but it was the moment that proved Webb could actually do exoplanet atmospheric chemistry from 1 million miles away, and everything since has built on that first result. From there, the discoveries started stacking up quickly. Webb studied the exoplanet WASP-107b and found water vapor, sulfur dioxide, and something genuinely strange: clouds made partly of sand, deep in its puffy, extended atmosphere. Sand, on a planet, detected not by sending a probe, but by analyzing starlight filtering through that planet's atmosphere from unimaginable distance. Then came TOI 561b, a scorching fast orbiting rocky world once thought too extreme and too battered by its own star to hold onto any atmosphere at all. Webb found evidence of a surprisingly thick one anyway, forcing scientists to rethink what kinds of planets can actually hang onto their air under brutal conditions. Then in 2026 alone, the pace didn't slow down at all. Webb examined a rare giant exoplanet and found its temperature was, strangely, remarkably close to conditions we'd consider familiar here on Earth, a genuine surprise for a planet of that size and type. And in one of the more visually stunning results of the year, astronomers used Webb to directly observe a hot Jupiter-class planet where clouds made of vaporized rock form and disappear in a daily cycle, essentially weather, real weather, playing out on an alien world 700 light years away, published in the journal Science, as one of the first times scientists have directly watched cloud cycling happen on a planet outside our solar system in real time. Now here's the discovery that gets the most attention online, and it's also the one that gets the most misrepresented. So let's slow down and get this one exactly right, because clickbait has absolutely mangled this story across the internet. In 2023, and again with stronger data in 2025, a research team using Webb reported tentative signs of a gas called dimethyl sulfide in the atmosphere of K2-18b, a planet that might be covered by a global ocean beneath a hydrogen-rich atmosphere. Dimethyl sulfide matters because, on Earth, it's produced almost exclusively by marine life, mostly phytoplankton. That's why the moment this made headlines, alien life started trending everywhere. Here's what actually happened scientifically, without the hype. The original 2023 detection was weak, statistically speaking, only reaching a confidence level scientists call 2 sigma, meaning there was still a meaningful chance the signal was just noise rather than a real detection. The 2025 follow-up pushed that up to roughly 3 sigma, better, but still well short of the 5 sigma threshold that astronomers require, before calling something a confirmed discovery rather than a promising hint. And crucially, multiple independent teams have since gone back and reanalyzed the exact same raw data using different methods. Several of those reanalyses, including ones that combined all of Webb's relevant instruments together into one joint study, found insufficient evidence to support the original claim at all. One particularly thorough study concluded that what looked like a signal in the mid-infrared data was more likely just instrument noise, not an actual chemical fingerprint from the planet's atmosphere. So where does that leave K2-18b, honestly? Not confirmed? Not disproven either, technically. Genuinely still an open, actively contested question inside the scientific community, with serious researchers on both sides of the debate. If you see a headline anywhere claiming NASA has confirmed alien life on this planet, that headline is false, full stop. And it's worth being skeptical of any source pushing that framing as settled fact, because the actual scientists working on this data are nowhere near that certain, and they're on the record saying so. Let's move from distant planets to something that came from outside our solar system entirely and actually passed through our neighborhood. In July of 2025, astronomers spotted only the 3rd confirmed interstellar object in recorded history, a comet given the name 3I/Atlas, and Webb turned its instruments toward it to figure out exactly what it was made of. The results were stranger than anyone expected. Webb found the comet's surrounding cloud of gas, called its coma, was dominated overwhelmingly by carbon dioxide, with a ratio of carbon dioxide to water among the highest ever measured in any comet observed, from inside our solar system or otherwise. Alongside that, Webb picked up water ice, carbon monoxide, and a tentative trace of a sulfur-based gas. Then things got even stranger. A separate analysis of the comet's trajectory, the steep angle at which it's cutting through our solar system, suggests this object could be roughly 7 billion years old, which would make it about 3 billion years older than our entire solar system itself. 3 billion years. 3. This comet was likely already ancient before our sun had even finished forming. Follow-up work using ground-based telescopes measured unusual ratios of carbon and nitrogen isotopes in the comet that further support the idea that it formed somewhere very different, chemically speaking, from anything we're used to seeing in our own cosmic backyard, likely flung out of its home system by a passing star, long, long ago, wandering alone through interstellar space for billions of years before we ever noticed it drifting through. Webb hasn't only been looking outward at distant objects either. It's turned its instruments on planets much closer to home, too. Using Webb's data, scientists finally solved a genuine decades-old mystery about Saturn, specifically a strange shifting pattern in how fast different parts of the planet appeared to rotate, a puzzle that had confused planetary scientists for years. It turned out the cause wasn't what almost everyone had assumed for decades. Webb also spotted a completely new feature never seen before in Jupiter's atmosphere, a high-speed jet stream spanning thousands of miles, hiding in plain sight the entire time, simply invisible to earlier telescopes that couldn't see it clearly in the wavelengths Webb specializes in. Zooming back out to the largest scales imaginable, Webb has also been used to map something you can't actually see at all: dark matter, the invisible material that makes up most of the universe's mass but doesn't interact with light in any way we can directly detect. By observing how the light from extremely distant galaxies gets bent and distorted as it passes near massive foreground objects, a phenomenon called gravitational lensing, scientists using Webb built one of the most detailed, highest resolution maps of dark matter distribution ever produced. The map reveals dense clumps of dark matter connected by thinner filaments, forming a vast web-like structure stretching across space, a structure that shapes where galaxies actually form in the first place. Webb's superior resolution revealed this cosmic web far more clearly than the equivalent Hubble data ever managed to, giving researchers their sharpest look yet at the invisible scaffolding holding the visible universe together. Star formation itself, the actual birth of stars inside clouds of gas and dust, is another area where Webb has quietly produced some of its most important work. even when it doesn't always make flashy headlines. Its infrared vision cuts straight through the thick dust clouds that block visible light entirely, revealing stars in the earliest stages of formation that were completely hidden from every telescope that came before it. Regions like the Carina Nebula, previously studied for decades, suddenly revealed entirely new layers of detail once Webb turned its instruments toward them, showing intricate structures of gas and newborn stars that simply weren't visible before. In 2026 specifically, astronomers used Webb to identify, for the very first time, the actual progenitor star behind a supernova in a nearby galaxy, something no other telescope on Earth or in orbit had managed to pull off. The star responsible turned out to be a red supergiant sitting in an unexpectedly dusty environment, the kind of dust that would have completely hidden it from conventional telescopes, looking in visible light. Around the same time, Webb produced striking new imagery of Messier 82, a galaxy undergoing rapid, intense star formation roughly 12 million light-years away, revealing structural detail inside it that had simply never been resolved this clearly before. Also in 2026, researchers combined new Webb observations with over a decade of existing Hubble data to confirm something genuinely new, an entire class of ancient stellar objects inside our own Milky Way, nicknamed bulge fossil fragments. One particular object, called Terzan 5, turned out to be a surviving relic from the earliest days of our galaxy's formation, a primordial clump of stars that somehow avoided merging into the rest of the galaxy's central bulge the way similar structures did billions of years ago. It's essentially a fossil sitting inside our own galactic backyard, holding clues about how the Milky Way itself came together in its earliest, most chaotic period. Even Webb's study of black holes has produced results that challenge existing assumptions about how the universe works. Researchers used Webb to map the motion and chemical composition of gas orbiting a black hole inside a tiny, extremely distant galaxy, one so far away that its light has been traveling toward us for more than 13 billion years. What they found suggests this particular black hole, containing roughly 50 million times the mass of our Sun, may have actually predated the galaxy surrounding it, potentially forming within the first second after the Big Bang itself. That's a genuinely radical idea, because the standard assumption has always been that galaxies form first and black holes grow inside them afterward, not the other way around. Stepping back from all of these individual results, what actually connects everything on this list is the same underlying capability. Every single discovery here, from the earliest galaxies to the oldest known comet to the atmospheres of planets we'll never visit, comes down to Webb's ability to detect extremely faint infrared light with a level of precision no instrument before it could match. That's not a small technical detail. It's the entire reason this telescope exists in the first place, and it's why nearly every result on this list starts with some version of the same sentence. Scientists had suspected something like this might be true, but they needed Webb's specific capabilities to actually confirm it, or in some cases, to discover something nobody had even predicted looking for. It's also worth being honest about what Webb hasn't done, because separating real discoveries from internet hype matters just as much as listing the real ones. Webb has not confirmed alien life anywhere, despite what certain corners of the internet insist. Webb has not broken cosmology in some catastrophic physics-ending way, even though the impossible galaxies problem is a genuinely serious open question that current models haven't fully resolved yet. And Webb hasn't found evidence of anything artificial, engineered, or intelligently designed anywhere in its observations, despite recurring claims that circulate whenever a new object like 3I/Atlas shows up looking unusual. What Webb has actually done is arguably more impressive than any of those exaggerated claims because it's real, it's measured, it's published, and it's still ongoing. That last part matters more than people realize. This isn't a finished list. Webb is still up there right now, still gathering data every single day, still pointed at targets astronomers have been waiting years to get a clear look at. The mystery of the impossible early galaxies is still unresolved. The debate over K2-18b is still actively playing out in scientific journals as different teams reanalyze the same data with different methods. The interstellar comet 3I/Atlas is still being tracked as it moves back out toward interstellar space, with researchers racing to learn everything they can before it disappears from view for good. Every one of these open threads could produce another major headline within the next year, and there's no way to predict exactly which one breaks next. So if you're wondering what's coming after this list, the honest answer is that nobody fully knows yet, and that's actually the exciting part. Webb was built with a design life of at least 5 to 10 years, potentially longer depending on how efficiently its fuel gets used, and every year it stays operational is another year of data pushing back against the edges of what astronomers thought they understood. The telescope that already found a comet older than our solar system, mapped invisible matter across the cosmos, and forced physicists to argue about galaxies that shouldn't exist yet, is nowhere near finished. It's just getting started, And everything on this list is really just the opening chapter of a much longer story, still being written one observation at a time. Think about the sheer scale of what's been covered here for a moment. A single instrument, sitting 1 million miles from Earth, has managed to touch nearly every branch of astronomy that exists: cosmology, through the earliest galaxies; exoplanet science, through dozens of atmospheres analyzed one by one; solar system science, through Saturn and Jupiter; small body science, through an interstellar comet older than the Sun itself; stellar astrophysics, through star formation and supernova progenitors; galactic archaeology, through ancient fossil star clusters hiding inside our own galaxy; and fundamental physics, through black holes that may have formed before the galaxies that host them. No single telescope in the history of astronomy has managed to move the needle across that many fields simultaneously in such a short operational window. Part of why that's even possible comes down to a design choice made decades before launch: infrared as the primary wavelength of observation. Visible light, the kind human eyes and most earlier telescopes are built around, gets absorbed and scattered by dust clouds scattered throughout the universe, effectively blinding earlier instruments to anything hidden behind that dust. Infrared light passes through that same dust largely unaffected, which is exactly why Webb keeps finding things that were technically always there, just invisible to everything that came before it. The newborn stars inside the Carina Nebula weren't secretly created the moment Webb looked at them. They were always forming there, hidden behind a dust curtain no earlier telescope could see past. Webb didn't create new objects in the universe, it simply pulled back a curtain that had been blocking our view the entire time. That same logic explains why the earliest galaxies took so long to find too. Light from objects that far away has been stretched by the expansion of the universe itself, a phenomenon called redshift, which pushes visible light from those ancient galaxies all the way down into the infrared range by the time it finally reaches us. A telescope, built primarily for visible light, no matter how powerful, would simply miss most of that light entirely, because it's not looking in the right part of the spectrum in the first place. Webb was purpose-built to catch exactly this kind of stretched ancient light, which is precisely why it succeeded where Hubble, an incredible telescope in its own right, physically couldn't reach nearly as far back in cosmic time. None of this happened by accident, and none of it happened quickly either. Webb spent decades in development, faced repeated delays, ballooned significantly over its original budget, and survived multiple points where the entire project nearly got canceled before it ever reached the launch pad. The fact that it now sits perfectly positioned 1 million miles away, its enormous gold-coated mirror unfolded exactly as engineers designed it to, delivering results at this pace and this consistency, is itself something close to an engineering miracle, entirely separate from the scientific discoveries it's been producing since it opened its eye on the universe. So when someone asks what Webb has actually found so far, the honest answer isn't a single headline, it's a sprawling, still-growing body of evidence touching almost every open question in modern astronomy at once. Some of it, like the carbon dioxide detection on that very first exoplanet back in 2022, feels almost quaint now compared to what's followed. Some of it, like the impossible galaxies problem, is going to take years, maybe decades, of additional observation and theoretical work before anyone fully understands what it means. And some of it, like the debate over K2-18b, might never resolve cleanly at all, remaining a genuinely contested scientific question for years to come. The kind of open mystery that keeps entire careers occupied, chasing an answer that stays just out of reach. That uncertainty isn't a weakness in the story, it's actually the most honest part of it. Real science rarely wraps up in a single tidy headline. It's messy, it's contested. Researchers disagree with each other in public through competing papers, and conclusions get revised constantly as new data comes in. Webb hasn't handed humanity a finished picture of the universe. It's handed us a much sharper, much more detailed set of questions than we had before, and in a lot of ways, that's a far more valuable thing for a telescope to produce than easy answers ever could be. There's a whole category of results worth adding here too, because the exoplanet list runs even deeper than what's already been covered. Around the young, dusty star Fomalhaut, Webb was originally sent to look for a suspected asteroid belt, and it found one, but it also found something nobody was specifically looking for. A far more complex structure of overlapping dust belts than anyone expected, hinting at unseen planets, sculpting the debris through their gravity alone, without those planets ever being directly photographed. Around the star system Beta Pictoris, long studied for its dramatic edge-on debris disk, Webb's more recent observations uncovered a previously hidden planet tucked inside that disk, a discovery that had eluded astronomers despite decades of prior study with earlier telescopes. Closer to a star system many people have actually heard of, Webb turned its instruments toward Alpha Centauri A, the nearest sun-like star to our own solar system, sitting just over 4 light-years away. The results provided strong evidence pointing toward a giant planet orbiting that star, An exciting possibility, precisely, because of how close and how similar to our own sun that star actually is, though confirming a planet at that distance remains an ongoing delicate process rather than a done deal. Then there's the TRAPPIST-1 system, home to 7 roughly Earth-sized rocky planets packed tightly around a small, dim red dwarf star, long considered one of the most promising nearby targets in the search for potentially habitable worlds. Webb has been systematically working through the atmospheres of these planets one by one, checking each for signs of a genuine atmosphere at all, since red dwarf stars are known for blasting their planets with intense radiation that can strip atmospheres away entirely. Early results have been mixed and are still ongoing, with some of the inner planets showing no strong evidence of a substantial atmosphere so far, while observations of the outer planets in the system continue. And on WASP-39b, a puffy, Saturn-mass planet orbiting close to its star, Webb delivered the first clear detection of sulfur dioxide ever found in an exoplanet atmosphere, a molecule that forms through photochemistry, meaning it's created when starlight actually reacts with and rearranges the chemistry of a planet's upper atmosphere. Finding it confirmed that these kinds of chemical reactions, well understood here on Earth, also play out on worlds hundreds of light years away, exactly the way physics would predict they should. It's worth pausing here to appreciate just how different this exoplanet work is from almost everything else on this list. Distant galaxies and ancient comets are each essentially one-time discoveries, remarkable but singular events tied to one object. Exoplanet atmospheric study is closer to a running experiment, planet after planet, star system after star system, slowly building toward a genuine catalog of what kinds of atmospheres exist across the galaxy, which planets manage to hold onto theirs, and which get stripped bare by their host stars. That accumulating data set, more than any single headline result, might end up being one of Webb's most lasting scientific contributions, once its mission eventually winds down years from now. The telescope itself deserves a moment of attention too, separate from what it's actually discovered, because the engineering behind it is arguably just as remarkable as the science it produces. Its primary mirror spans over 21 feet across, built from 18 individual gold-coated hexagonal segments that had to fold up like origami to fit inside a rocket, then unfold with perfect precision once in space, a process with hundreds of individual points of potential failure and zero chance of a repair mission if something went wrong, unlike Hubble, which orbits close enough to Earth that astronauts could physically service it over the years. Webb sits roughly 1 million miles away, far too distant for any crude repair mission, meaning every single deployment step had to work correctly on the very first attempt, with no do-overs available if something jammed or tore. That mirror is paired with a tennis court-sized sunshield, 5 incredibly thin layers stacked beneath the mirror, designed to block heat and light from the sun, Earth, and Moon simultaneously, keeping Webb's instruments cooled to nearly absolute zero. That extreme cold isn't a minor technical detail. It's absolutely essential to the entire mission, because any warmth in the telescope's own instruments would swamp the extremely faint infrared signals arriving from billions of light years away, effectively blinding it with its own heat. Getting that sunshield to unfold correctly, layer by layer, without a single tear or snag, was considered one of the single riskiest moments of the entire mission timeline, and it succeeded on the first real attempt. All of that engineering effort exists purely to serve one purpose: collecting as much extremely faint infrared light as physically possible, then feeding it into instruments sensitive enough to pull out chemical signatures from atmospheres of planets that are themselves invisible to direct imaging in almost every case. Every discovery already covered in this list, from ancient comets to distant galaxies to exoplanet clouds, ultimately traces back to that same underlying capability, refined over more than 2 decades of design and construction before the telescope ever left the ground. It's also worth remembering that Webb doesn't operate alone. Many of its biggest results only became fully convincing once combined with data from other telescopes and instruments, both in space and on the ground. The dark matter mapping work leaned on comparisons with older Hubble imagery of the exact same patch of sky. The interstellar comet research combined Webb's infrared spectroscopy with ground-based optical and isotope measurements from telescopes like the Very Large Telescope in Chile. The ancient stellar fossil fragments inside our own galaxy were confirmed only after combining brand new Webb observations with over a decade of prior Hubble data on the same target. Webb tends to work best as part of a much larger, coordinated effort across multiple instruments and research teams worldwide, rather than as a lone telescope operating in complete isolation from everything else astronomers have built and gathered over the decades before it. Looking ahead, there's already discussion of what comes after Webb, with early planning underway for a future mission, sometimes referred to as the Habitable Worlds Observatory, aimed specifically at directly imaging Earth-like planets around nearby stars and searching their atmospheres for genuine signs of life. learning directly from both the successes and the limitations Webb has already revealed. That mission remains in early planning stages, likely years or even decades away from launch. But its entire design philosophy is being shaped in large part by exactly the kinds of questions Webb has raised without fully answering, including the ongoing unresolved debate over K2-18b and what it would actually take to confirm a biosignature with real scientific confidence rather than a statistically shaky hint. If you found this rundown useful, that was the entire goal, cutting through the noise and clickbait headlines to show you what Webb has actually, verifiably found, backed by real published research instead of speculation dressed up as certainty. Not manufactured drama, not invented confirmations, just what the instruments actually measured, checked against what the scientists who actually built and operate this telescope are willing to put their names on in published journals. There's a lot more coming. Webb is still up there right now, still working, still pointed at something new, still capable of turning next month's routine observation into next year's biggest headline.